a very renowned scientist, and she is also the president of the National Academy of Sciences, United States of America. Respected Professor Shekhar Mande, Director General CSIR, Secretary DSIR, and also MOES. We are very fortunate to have the head of our family with us today. Respected President of INSA, Professor Chandrima Saha, we are very happy to have you with us. Respected former directors, Professor Harsh Gupta and Professor Dimbri, and respected Chairman of RC, Professor Goel, and members of the Research Council, senior colleagues, scientists, staff, ladies and gentlemen. It's indeed a very great day for us as we are nearing the conclusion of the Diamond Jubilee celebrations of CSIR National Geophysical Research Institute, which has 60 years of tremendous scientific achievements, which we have celebrated over various events during the year, and we are reaching the concluding stage, which is next month. So this particular lecture is the last in the monthly Diamond Jubilee, and I'm very, very happy that such an eminent person like Professor McNutt has kindly agreed to deliver this talk. And what a topic! I mean, it's such an impressive and exciting topic, a general topic relevant to one and all. In fact, we have received several phone calls appreciating and congratulating us for organizing this such a wonderful talk. So at the outset, I would like to thank you, Professor McNutt, for agreeing to be with us on this very auspicious day. Thank you very much. And before we go to the next item, I would like to briefly state that this year has been a year of celebration for us, in spite of the COVID pandemic, which has tried its best to stop our efforts. But I can assure you that all the colleagues of NGRI have worked hard to make this a very memorable year. We have a complete facelift of the entire campus, the buildings. We have had a wonderful lecture series, as you know, and we have also tried to bring about a lot of changes, especially trying to address the scientific future of this institute. Our attempts have been to identify the most potential zones of geoscience research. We are also trying to invite eminent scientists from all over the world to come and spend time with us, and actually with the intent of starting state-of-the-art new groups, new divisions, new research areas. And this has been a very exciting exercise, I must say. And we are also planning several activities on the 11th of October. Maybe I shall keep some of it as a suspense and not reveal all of it. But certainly some very interesting things have been happening. And we are so grateful to Professor Mande, our Director General. He has been very, very supportive. In fact, he has been with us physically, even in these very difficult times. He has come and he has encouraged us for this very auspicious Diamond Jubilee celebration year. And I am also very grateful that our director has been on this constantly so that we make it a very successful affair. So with these few words, I would like to set the program rolling. And before we request the speaker, I would like to request Dr. V.M. Tiwari, Director of CSIR-NGRI, to kindly introduce our Honorable DG and also the eminent speaker of the day. Dr. Tiwari.
Thank you, Dr. Rao, the Chairman of the Celebration Committee. Distinguished Speaker of the Day, Professor Marcia McNutt, President, National Academy of Sciences, United States of America, Professor Shekhar Mande, Secretary to the Government of India, Department of Scientific and Industrial Research, and Ministry of Earth Sciences, distinguished chair and members of the CSIR-NGRI Research Council, Professor Goyal, Professor Singhvi, Professor Tandon, many of them I could see joining this talk today. Former directors of the CSIR-NGRI, Professor Gupta, Professor Dimdi, directors of the various geoscientific institutions in the country, I could see Dr. Mahapatra, DGGSI, and others. My dear colleagues from CSIR-NGRI, students, and several guests joined through online platform. Namaskar and very good morning to our distinguished speaker and good evening to all others. Today, we are having the 10th talk, as Dr. Poon-Chandra has told, the last talk of the CSIR-NGRI Diamond Jubilee series. There would not have been a better person than Professor McNutt, who have honored us by accepting our invitation to speak on this historic occasion of India's largest geoscience research institute. We are equally delighted by the gracious presence of Professor Mande, the head of the CSIR family, and many distinguished scientists, including the President of Indian National Science Academy, Professor Shah. You may recall that this lecture series was started with a talk by Professor Enika Junev, FRS, another very globally known geophysicist, and fortunately, Dr. Mande had again resided on that day. First, we are very much grateful to both of these distinguished colleagues who joined today with us. For the benefit of the guests today, I would like to speak few words about CSIR-NGRI, which is established 60 years back in 1961 and contributed more than 100 books, encyclopedia, more than 5,000 papers in the SCI journals, leading journals in science and nature as well. Today, CSIR-NGRI publishes highest number of papers in geosciences from India. Several of its scientists, besides being recognized by national and international science academies, they have contributed towards several of the national priority programs for the benefit of the society. Our future research efforts are designed towards deep earth and near surface explorations. I will not explain more because while I remember the report which was submitted by Professor McNutt as a ocean exploration to then President in 2001 as a chair, and define what difference between exploration and research is, which are critical to understand processes responsible for shaping Earth's structure and dynamics and for the sustenance of the life on the Earth, respectively. I am also privileged and honored to introduce today's speaker, Professor McNutt, and guest of honor, Professor Mande, though both of them do not need any introduction to this audience. Professor McNutt is well-known geophysicist who had the distinction to be a first woman director of US Geological Survey during 2009 to 13, and the first woman elected to serve as a president of United States National Academy of Sciences, and she's serving since 2016. I know Professor McNabb since I started my PhD on gravity and first woman director of US Geological Survey during 2009 to 13, and the first woman elected to serve as the president of United States National Academy of Sciences, and she's serving since 2016. I know Professor McNabb since I started my PhD on gravity and isostacy. However, I had a chance only to meet her through my postdoc advisor, Michelle Diamo, during 2000. And that time, she was already a very known person and president of American Geophysical Union. She has completed her PhD in Earth Sciences in 1978 from Scripps Institute of Oceanography on the topic continental and oceanic isostacy. In the same year, she has published papers in EPSL, JGR, and Science from her PhD. And probably many of the geophysicists who know and still use the code and often known as the Parker code, and she co-authored with Parker in 1978. Apart from having a large number of publications in leading journals and also being editor of several journals, including for 3 years the senior editor of Science. He also had been holding several distinct positions in the university and academia. He was director of MIT Woods Hole Institute of Oceanography, Joint Program in Oceanography and Allied Ocean and Engineering Sciences, President and CEO of Monterey Bay Aquarium Research Institute. And this research institute is very different in the present era. We know that how there is a need of public-private partnership being talked about in research. And this institute is one among such kind of the endeavor made by the people in early 1900s. She had been a professor at Scripps Institute, Stanford University. She was presently she is a professor at Georgetown University. The list is very long, and most of you can see her CV from Wikipedia, from many other things, but few of things which I would like to point out. One of them is her report, which she has submitted as chair to then president in 2000, and that has made headlines in many newspapers regarding the ocean exploration and giving weightage to the ocean exploration as much as the space sciences. She had served many of the committees across different parts of the world and worked also in the different areas of geophysics. The professional activities, if we see at least more than 100 committees, he had either chaired or served. She also been a very prolific speaker and speaker on demand and delivered a large number of lectures across the different societies and in different meetings at different institutions. I will not dwell upon much about Professor McNutt, and I would briefly talk about the guest of honor today, Professor Shekhar C. Mande, a physicist turned structural and computational biologist who received his PhD in molecular biophysics from Indian Institute of Science, Bangalore. He had been working outside India as a postdoctoral fellow and different positions at Rijkswaterstaat Groningen in Netherlands, as well as other places in US, and joined afterwards as a scientist at CDFT. He rose to the position of the Director, National Center for Cell Biology in Pune under Department of the Biotechnology, and currently he is serving as the Director General of Council of Scientific and Industrial Research and Secretary, Department of Scientific and Industrial Research, Government of India, as well as Secretary, the Ministry of Earth Sciences on additional charge. He had also been awarded several honors and awards, including the highest scientific honor, Shanti Swaptu Bhatnagar Prize, and he is a fellow of three very distinguished Science Academy of India. I forgot to mention about Professor McNutt that he is fellow of American Geophysical Union. He is fellow of Royal Society of United Kingdom. He is, of course, fellow of National Academy of Sciences and other science academies of United States. So with this, I will first request Honorable Director General Dr. Shekhar C. Mande to give his few remarks on this occasion. Dr. Mande, it's over to you.
Thank you, Viren, so very much. Professor Marcia McNutt, President of the National Academy of Sciences, USA. My close friend and colleague, Chandrima Shah, President of the Indian National Science Academy. Another close friend, Viren Tiwari, Director of the National Geophysical Research Institute. All the senior colleagues and friends who have joined here, members of the CSIR-NGRI family, and members of the extended family of CSIR-NGRI. It's a great pleasure to be able to be present on this particular occasion. Good evening to all of you, and a very good morning to Marcia. It's a pleasure to have you, Marcia, with us. And please take today's lecture as an open invitation that whenever you would wish to come to India and spend some time with us, we'll be delighted to host you in any of our institutes. As you would know, CSIR is a chain of about 37 laboratories across India. The last 1 year, all of you would agree with me, has been an extraordinarily challenging year for humanity in general across the globe. And there are several learnings from this last 1 year, what we have gone through. One of them, of course, is that science and science alone can provide solutions for most problems that humanity faces today. That's one of the great learnings. And in fact, I'm glad that societies around the world also recognize that particular fact. But another interesting thing that we have realized is that the value of all of us working together, many different nations, within the nations, many different organizations, industry, academia, and society at large, if we work together, the science that we do is a very powerful vehicle to provide these solutions. And I'm glad that India and US, and particularly the National Academy of Sciences US and Indian organizations have had a very close relationship over the years. I have had myself the fortune of attending the Frontiers of Sciences lecture that are organized every 2 years by the Indo-US Science and Technology Forum. And that took me to Irvine to attend one of those lectures, lecture series in those days when I was still young. It's so good to have both the leaders of Indian academies here, Marcia and Chandrima. And with both of you together, we can resolve to work even closer in the coming time so that the even more difficult challenges that humanity faces, once we come out of COVID, we can start tackling them together. So it's great to have you, Marcia, along with all of us. And I don't want to take too much time of all of you. I don't want to stand between you and a lecture. I will stop here and thank you very much. All the best to all the CSIR-NGRI family members on the Diamond Jubilee. Thank you.
Thank you very much, sir. May I request Professor McNabb to deliver her lecture?
Absolutely. Thank you so much for this opportunity, and congratulations to the National Geophysical Research Institute on their Diamond Jubilee. This is truly a milestone, and I am honored by the introduction I have received and by the distinction of the audience for this lecture. So the title of my talk today, Civilization Saving Science for the 21st Century. I'd like to lay out a roadmap for how the geosciences can contribute to some of the greatest perils that society is facing right now. For example, as scientists, we fear that there's simply not enough clean water, arable land, mineral deposits, and other natural resources to continue current levels of consumption unabated, and much less provide similar levels of consumption for the much larger population of citizens in nations that are developing and aspire to similar prosperity as the developed nations. At the same time, the growing impacts of climate change are also threatening species and in multiple ways and societies, from shrinking the livable land space to increasing the severity of extreme weather and wildland fires, promoting mass human migrations, and more subtly, but just as worrisome, climate change is occurring at a rate that outpaces the ability of most organisms to naturally evolve. And this is compounded by the fact that human fragmentation of landscapes precludes much species migration, thus disrupting the functions and the rhythms of natural systems that humans rely on for food and other ecosystem services. Now, most of these issues that I've just mentioned, resources, climate, sustainability, fall squarely in the domain of the earth sciences. Science of clean air, clean water, soil conservation, energy resources, extreme weather, all of those have been mainstays in geoscience education and research. But I'll argue today that the current course of earth science education, research, and partnerships is inadequate if we hope to solve the problems of our time and reach a sustainable state here on Earth. I've heard some say that sustainability and conservation are all about saving the planet. But from observing the history of deep time, that is simply not true. Earth will survive climate change. It will survive deforestation, species extinction, sea level rise, and pollution. After all, similar plagues and worse are recorded in Earth's geologic past. But the real question is, will we? The rise and fall of modern human society could become nothing more than a brief event horizon in the planet's rock record, thicker and dominated by plastic as compared with the iridium layer that marks the end of the age of the dinosaurs. But we will be fleeting nonetheless unless we take action. Now, geoscientists have used their expertise to seek out and quantify Earth's current resources, both renewable and non-renewable, and have monitored trends with time. However, the solutions to resource limitations, climate change, and preserving the intact ecosystems that provide clean air and water, and for the biodiversity that allows these ecosystems to properly function, will require a new way of working, a convergence in the earth sciences. And by convergence, I mean a cooperation and partnership with engineers, physical sciences, life sciences, and social sciences. So, what is convergence? Convergence published this policy forum that laid out the opportunities that would be enabled by a new way of thinking and discussed ramifications for educational funding and research enterprise. This was authored by Phil Sharp and Bob Langer, who were two colleagues of mine at MIT, and they challenged the research community to break down the disciplinary walls that prevent us from actually solving the problems of our time. So their argument was that multidisciplinary thinking and analysis will permit the emergence of a new scientific principles and opportunities. And I believe they were right. So what is convergence? Here's the cover of an Academy report on convergence. Convergence is defined as the integration of engineering, physical sciences with computation and life sciences, such as to have profound benefits for medicine, health, energy, and of course, the environment, which is the topic of my talk today. This term originated as a third revolution in biomedicine and was originally proposed as a way to make healthcare more affordable. Now, convergent research is not the same as interdisciplinary, and I've contrasted the two in this table in terms of what quality is in the research and how it functions under interdisciplinary research and how it functions under convergent research. So if we look at education, in interdisciplinary research, students follow standard disciplinary curricula, but can be bridges by virtue of elective coursework. In convergent research, students are educated in a highly complex, multidisciplinary problem solving that makes them very nimble at understanding the vocabulary and the approach to problem solving of different disciplines. In terms of research, in interdisciplinary work, researchers approach a problem from more than one disciplinary dimension. Whereas in convergence, it's truly transdisciplinary, integrating knowledge, tools, and ways of thinking from multiple disciplines. In terms of physical space, researchers still reside in conventional departments in interdisciplinary research, although they often set up transient and often virtual centers to provide a focus for interdisciplinary problem solving. In convergent work, researchers reside in multidisciplinary institutes that span science, engineering, and social sciences, including public policy. And the funding is different too. Funding typically flows through disciplines in interdisciplinary research, and because of that, it puts projects in multiple jeopardy of failing if any one aspect is not supported through its disciplinary channel. Whereas in convergent research, special funding programs are devoted to convergent research projects, regardless of disciplines, allowing the submission of one proposal to cover all investigators. So what are some of the big important breakthroughs that have emerged as a result of convergent research? Well, examples abound in health, nanotechnology, biotechnology, information technology. I've just suggested a few here. The first on my list is the creation of cyber-physical systems, which are smart network systems with embedded sensors, embedded processors, and actuators that are designed to sense and interact with the physical world. One of the most profound examples of this is precision agriculture, where agricultural fields are monitored with embedded sensors to allow for more efficient use of water and fertilizer based on what the sensor network is saying. Another example is synthetic biology, which is constructing new biological entities and redesigning existing ones. And examples are current efforts to improve photosynthesis as a way to make plants more productive and also, of course, address climate change. And my last example here is nanotechnology, which is manipulating proteins in crystals into nanoscale structures for specific purposes. And there are many examples of the creation using nanotechnology of nanoparticles that serve as catalysts to boost chemical reactions. And again, this is something that could be of a benefit to climate change if these nanoparticles can increase the efficiency of carbon capture and storage. Now, just to show what the impact can be from the adoption of convergence, Phil Sharp, in his presidential address to the AAAS, linked convergent science to the economic resurgence of Cambridge, Massachusetts. And he marked on this map all these labs that have grown up in this area and partially for the reason of taking advantage of the convergent research going on. And Eric Lander recently quoted to me that there's some $20 billion in economic development that came out of the Broad Institute alone in Cambridge. So clearly this is something that is not only an approach that not only addresses the societal problems of our time, but can create huge economic expansion. So what I'd like to argue today, that these current approaches could extend to the geosciences. And in fact, I will argue that they were already there. Convergent approaches were being used in the geosciences even before Sharp and Langer wrote their landmark paper. And the best example is saving lives from destructive earthquakes. Of course, earthquakes are unpredictable. Hundreds of thousands can perish in a single event, and they have huge human impacts: death from collapsing buildings, exposure from the homelessness, and secondary effects from the failure of infrastructure. We saw this, of course, play out with headlines from Port-au-Prince in Haiti. Now, back in 2003, the National Academy produced this report, Living on an Active Earth, Perspectives on Earthquake Science, in which they argued that the way earthquake science was proceeding included disciplines such as geology, paleoseismicity and tectonics, geophysics, looking at strong ground motion and heat flow, geodesy, rock mechanics, mathematics with big data analysis, structural engineering, architecture, public policy, economics, and communications, that all of these had come together in the geosciences to address the problem of earthquake risk reduction and resilience. And just as an example of how this worked, the U.S. has step by step increased its resilience to earthquakes despite high exposure. The map on the left shows a hazard map from the U.S. Geological Survey showing in red areas of highest seismic risk and in white the areas of lowest. Starting with this hazard map that was a combination of mapping where are the faults and what is the strong ground motion from the largest earthquake that could be predicted to fall on those faults. The USGS worked with engineers to produce a report from the National Earthquake Hazard Reduction Program that recommended which buildings and what kind of buildings in what part of the country needed seismic provisions built into them from the start. Then the engineers worked with public policy people to create the International Building Code. Here's the 2012 version of it, but this is periodically updated as new mapping information comes forward. And through this, the infrastructure within the United States has year by year become more resilient to earthquakes. And now it's to the point where when an earthquake happens in the US, the expected death toll is very small to non-existent. And this is all from a convergence of the geosciences with engineering, communication, and public policy. We even created convergent earthquake organizations, such as the Earthquake Engineering Research Institute, which started as a nonprofit organization, was founded in 1948 as a national society to understand risk reduction and increase resilience. The disciplines included in this organization are engineering, geoscience, social science, architecture, planning, government, emergency management, public health, and policymaking. And being a starting as a national society, it could pull in the disciplines it needed, regardless of the silos that can exist in many universities. Another example is the USGS Natural Hazards Program. This is part of a government agency, the USGS, and it includes geodesists, geologists, geophysicists, social sciences, and engineers in order to create scientific advice to make our nation in the US more resilient to earthquake damages. Now, my argument is that convergence could benefit many other topics, not just earthquakes. Convergence in the geosciences could mitigate risks from other natural as well as man-made disasters. And the ones that seem to trouble society most right now are man-made. Climate change adaptation, climate change resilience, and of course, climate change mitigation, oil spill prevention and response, environmental health, and sustainability. And I'll briefly go through some of these examples. Environmental health. More than 10 million people die annually from environmental factors. The most common problems are air, water, and soil pollution, but there's also chemical exposure. Solutions involve eliminating the hazard or reducing personal exposure or improving the health response or, in some cases, doing all of them. So in order to make progress in environmental health mitigation, we need to have geoscientists who understand about soil and water and air, working with public health experts, experts in toxic chemistry, working in microbiology, which can often be the solution to the problem, and industrial engineering. Industrial engineering can both be a source of pollution and it can be a solution. Let me move on to climate change. We need questions to, or answers to questions such as how fast must we retreat from sea level rise? Better knowing how fast the seas are going to rise will determine whether we have to abandon facilities before their natural lifetimes from an engineering standpoint are reached. We want to know when can we expect yields from current crop varieties to start dropping, and what measures could maintain yields, such as synthetic biology, and or even developing new hybrid crops. And what will be the impacts of new patterns of flood and drought? I'm speaking to you today from California, and you've probably heard the news that this has been the worst wildfire season ever here in California, compounded by drought. And what will encourage people to take action? Very often, we know what people need to do, but getting them to do it is a harder problem. And so this requires a convergence for climate science of geoscientists working with ecologists, plant researchers, designers and architects, community planners, engineers, and psychologists to understand, why do people behave the way they do? Why are they not taking action that's in their own best interest? And I show here a picture just of a architectural design for a house that's made resilient against rising seas. And all the materials in this house are biodegradable. So if it should be washed away in an earthquake, it would not add to ocean pollution. Now let's go on to sustainability. Question here is, can we supply sufficient food, fresh water, energy, and raw materials for a growing population on a finite planet? And can we do so while maintaining quality of life? I will argue that science is the only solution we have for everyone to live better and not having some have to lose so that others can win. Science is the only approach we've ever had out of that zero-sum game. So the sorts of convergence that we need for sustainability are geoscientists working with geographers and with ecologists, agricultural scientists, historians, and engineers. All of these groups of experts have something to contribute to creating a more sustainable use of our resources. Convergence is also important in understanding cascading disasters. It is often that one disaster will lead to another one. We saw a good example of that with Fukushima, where the Tohoku earthquake led to a nuclear meltdown. How does a nation design resilience, and how does it design response with the possibility of cascading disasters? Another example is a flood can inundate a community, and then it leads to toxic chemical release in that community. And the toxic chemical release can become even more devastating than the original flood. Or drought leading to insect infestation. We're going to be seeing more and more cascading disasters, and we have to be creative in our use of partnerships to understand the linkages between these disasters. Related but slightly different than cascading disasters are compound disasters, where a slow-moving disaster like climate change increases the chances of coincident extremes in other disasters. For example, floods on the coastline becoming more extreme because of sea level rise, and storm surge, high tides, intense rainfall. All of those could be exacerbated by climate change. Or, as I just mentioned, forest fires more extreme from prolonged drought and extreme temperatures. So what do we all need to do to promote convergent thinking and convergent projects in the geosciences to address all these problems? Well, taking a play from the playbook of the biologists, what worked for them were dedicating institutions like the Whitehead or the Broad, developing special funding streams that allow one convergent project to be funded without having to individually fund the engineers and the scientists and the social scientists. You need enthusiastic and sympathetic university administrators because they have to create the promotion and tenure policies that will allow scientists working on convergence to thrive. We need education programs that teach convergent thinking, that radical integration of topics. And we also need high quality publishing outlets for convergent research. So in terms of dedicated space, here's a picture of the Broad. We need to bring researchers with diverse skills into proximity. All of you know from your time in academia that if you are in one department, it sometimes is hard to know who the good people are in other departments, much less get together with them to work on projects. And convergence institutes are the solution for that, but they often lead to duplicative space needed for universities with disciplinary traditions, so they can make it more expensive. I would argue that institutions like the National Geophysical Research Institute doesn't have that problem. You can naturally span disciplines without having to force yourself into departments that don't speak to each other. And some research labs have been created convergent from the very start. For example, Genelia Farms, which is funded by HHMI, is a convergent institute that includes mathematicians working on protein folding and biologists working on synthetic biology and social scientists all working under the same roof. You heard before that I was director of the Monterey Bay Aquarium Research Institute, or MBARI. That was also a convergent institute created by David Packard. And our important partner for the Research Institute was, of course, the Monterey Bay Aquarium, where the Monterey Bay Aquarium was the outreach for all the great discoveries of MBARI that came out from a convergence between science in marine biology, marine chemistry, marine geology, along with engineering to develop the new tools to explore the oceans in new dimensions. It was created convergent from the start. And of course, industrial research labs, and as I've just mentioned, government labs, might have more incentive and an easier path to convergence because they don't have to organize themselves around disciplines for education. Now, another barrier is funding. We need to cross the disciplinary silos that fund conventional research. For example, the National Science Foundation in the US has announced that growing convergence research is one of its 10 big ideas, and it is providing lots of funding for convergent research right now. And much of early funding in convergent research was non-federal. For example, the Howard Hughes Medical Institute funding Genelia Farms, or the Packard Foundation funding the Monterey Bay Aquarium Research Institute, and private philanthropists set up the Broad Institute in Cambridge, Massachusetts, which is a collaboration between MIT and Harvard. Industrial research labs and government labs can simply decide to support convergent teams and actually encourage it by putting their money into convergence and therefore incentivizing their scientists to create convergent teams. Another issue, though, is institutional culture. From the top down, the institution needs to buy into the culture of convergence. So if we look at promotion and tenure at many institutions, the first hurdle is generally you have to convince the experts in your discipline that you have done something important. And that view of how you fit into your field is usually focused on individual contributions, not team contributions, whereas there is no I in convergence. It has to be a team process. And of course, leaders at all levels control who gets hired in the first place. Do they hire someone who is focused on their discipline or someone who is interested in working in a convergent manner? They have to decide who gets what space, access to researchers and facilities, and discretionary funds. If the leaders don't buy in to convergence, it won't happen. So these are some of the hurdles that need to be overcome. Again, as I say, I think it's easier at a research institute than a university to do this. And education. Even at wonderful research institutions like the National Geophysical Research Institute, unless you have young people coming into the organization who can support convergence, you're not going to be able to build convergence into your institute. Students need a deep understanding in a convergent relevant discipline to be an asset to the Convergence team, but they also need to understand the language and the research approaches of other fields. And helpful approaches can be carving out time in undergraduate work for broad survey courses, but it has to go beyond that. It has to go beyond that to a radical rethinking of university education. And we also can teach young researchers to communicate without jargon. You mentioned previously about the Frontiers of Science that the National Academy of Sciences runs. And that is a wonderful place to learn how to communicate to leaders in other fields without using jargon. Awards can also stimulate convergence research. The Kavli Prize in Nanotechnology has held up and at the highest levels those who made breakthroughs in nanotechnology, and they recognize team behavior, unlike the Nobel Prizes, which tend to recognize individuals. The Kavli Prizes can honor teams. And the National Academy of Sciences has a James Prize, which is also targeted at convergence type research. But then where can convergent research be published? You really can't publish it in a disciplinary journal. For example, traditional disciplinary journals do not have the scope, the readership, or the reviewers to handle convergent research. Science played an early role in it, and I'll talk about Science Advances as having published some of the convergent work that is now coming out in the geosciences. So Science, for example, published this opinion piece on how MIT was going forward with convergence research. But Science Advances, here was a rapid assessment of disaster damage using social media activity. And this was a beautiful example of how convergence could work across from the geosciences to those studying social media. And this diagram on the left is taken from social media posts that were immediately after Superstorm Sandy came up the east coast of the US. And it showed that words such as governor, climate change, Sandy, no power, stay safe, FEMA, Frankenstorm, hurricane, right before the storm, there was very low use of these words. But in the days after the storm, you could see these words all being used at a high rate from Philadelphia on this side, New York, all the way through. And there was actually you could see that it was being used even in places like Portland and Seattle and Los Angeles, as everyone was picking up on this major event. And this just shows for the use of Sandy in New York and Chicago is the dotted line and Miami is the dashed line. You could see how it tailed off in the hours past it. So this is one way to understand what the impact of a storm is in different areas and how people are being impacted. And this was the predictive capacity of Hurricane Sandy, where they compared the social media with the actual impact of the storm and found a very close correlation. And then one other example I wanted to give is from the nation of Rwanda. And in this case, Rwanda had been doing national census at a very high cost. And the question was, could cell phone data be used to replace the census in Rwanda and save the nation a lot of money? And what they found was that, and this worked very well in Rwanda because there's only one cell phone carrier. What they found was they could use cell phone data to predict assets such as electricity, motorcycle, whether they had a television and a refrigerator, just by using cell phone data. So for example, you might ask, well, how do they predict whether someone has a motorcycle? Well, they can see how quickly the cell phone is moving from cell tower to cell tower. And if they have a means of transportation, then they can move more quickly between the cell towers. They compared the data with the cell phone data with the census data and found a very strong correlation between the two. I'm going to skip that because we're running out of time. So what sort of outcomes might ensue if we increased the use of convergence in the geosciences? Well, first of all, new partnerships between dissimilar disciplines and disconnected stakeholders would result, and society would benefit from that. There would be new career paths for students that would come out of this convergence. There would be new industries clustered around convergence institutes, just as what happened in Cambridge. And the geosciences are increasingly perceived as contributing to competitiveness, resiliency, health, and quality of life. Right now, I worry that the geoscientists are viewed as the doom and gloom people. They warn society about all the bad things that are going to happen, but don't necessarily figure out what can be the solutions. By using convergent research, geoscientists can become more of the solution. So geoscientists, therefore, would be widely perceived as part of the solution, not part of the problem. So I will end there, and I'm happy to take questions if there's any time, but I know time is running short. But I'm here and available.
Thank you. Professor Rao.
Yeah, thank you. I think that was an absolutely fascinating and fantastic lecture.
We are not able to hear you, Dr. Rao.
Pardon?
Yeah, now it's clear.
Yeah. Yeah, so I was saying that we are floored by a completely new concept and approach.
You are not heard, Dr. Rao.
Yeah. So, Marcia, I think you have beautifully highlighted the difference between interdisciplinary and convergent research, thereby breaking all barriers of discipline, and that really makes us to think. While we are struggling even to strike interdisciplinary alliances between institutes, so you have put forth a beautiful concept that it's not just interdisciplinary, but it has to essentially be convergent. I think that's a very interesting thing. And I'm also very thankful to you for showing us examples related to geosciences, particularly the seismic resilience slide that you showed was very, I would say, very impressive. And in fact, I would like to mention that the concept of convergent research that you mentioned is very much close to the Indian philosophy that we talk about unification rather than dissection. You know, in India, we talk about studying by unifying rather than dissecting objects. So I was really very pleased and happy to listen to your concept of convergence. And I think you made a very important statement about institutional culture. It takes years of effort to build any culture. And I think we start to think about your ideas when we build the next generation in our institutes. So that's really very interesting. And I also was very pleased to note that there are going to be new research opportunities and job opportunities for young people that come to do research in future. So with these few remarks, I would once again thank you very much for this wonderful talk. A lot of people have been watching you through YouTube and Facebook, and I'm sure there's a lot of take-home points from your talk. So thank you very much, Marcia. I hope you will be able to take a few questions from our...
Absolutely.
Yeah.
Absolutely. So, happy to take a few questions.
Yes. So may I start with Professor Sunil Singh, who is the director of NIO. Yes, Dr. Sunil.
Yeah, thank you very much, Poonchand-ji. And thank you, Professor Macknett, for fantastic talk. I would like to ask, as you were talking about this convergent science, I think our geology itself is a convergent science, because in geology or earth science, if you see, we are integrating so many things, say geology itself, physics, mathematics, biology, chemistry. So what do you have to say about that?
So this is why I think the geosciences will actually have an easier time, other disciplines, in actually embracing the convergence paradigm. For example, consider physicists. Physicists think of themselves as being the most reductionist. They go down to the smallest constituents of matter, and they build up the universe from that. It is possible to do cutting edge work in physics without actually knowing biology or probably much chemistry. Whereas if you're a chemist, you have to know physics, because if you don't know physical chemistry, you can't really get very far. So chemists are sort of the next step up, where they have to know physics in order to be good chemists. Biologists have to know all three. They have to know physics, they have to know some chemistry, and then, of course, about living systems in order to be a good chemist. Geoscientists have to know all four. They have to know physics, they have to know chemistry, they have to know biology, because so much of what is recorded in the rock record either tells us about life or has been created by life. And so geologists from the beginning understand much of the terminology and the way of viewing the world of all the other disciplines. And this is why I think that they will embrace it well. What I think has been missing in most geoscience departments that I know of is making that next step to the social sciences. Because we wring our hands and say, oh, why aren't people taking more action on climate change? But the truth is, for a huge personal decision. And it also is a decision that is slanted by the community in which they live. And I think we as geoscientists need to do much more effort to embrace the social sciences if we hope to actually get action on these plagues that are affecting society. So thank you for that question. It's a very good one.
Thank you very much.
Thank you, Marcia. I think Professor Shekhar Mande would like to ask the question. Sir, please.
Thank you, Marcia, for such a delightful presentation. I would like to a bit provoke on the same issue that you ended the last question with, is that if we take ourselves about 200, 300 or 400 years ago, all of us were philosophers, and as the time moved on, we started diverging from each other, so much so that it prompted someone like C.P. Snow to write an essay in 1962 on the divergent cultures that what we have. Has it happened unknowingly that we all have specialized so much in our cocoons that we have actually moved away from convergence, that we have to force ourselves upon convergence? And what do you think bringing out from the cocoons would actually require? As you know, that International Council of Science also has recently decided to actually integrate with Council of Social Sciences. But what does it take to really get ourselves out of the cocoon?
Okay, so wonderful observation about the fact that, back in the Renaissance, we had Da Vinci, who was making contributions across all of the sciences. And, I don't have the data to back this up, but my sense is that the reason we went from the ideal of the Renaissance scientist philosopher to a situation where everyone felt they needed to be deep experts in a very narrow field was the first of all, the explosion of knowledge that just made it difficult to truly recreate what Da Vinci was able to do, because you couldn't know everything about everything. But then there was still the celebration of the individual rather than the team. And so you can imagine that society could have gone one of two ways. One was to keep the ideal of the Renaissance scientist philosopher, but just not embody it in one person, but embody it in a team. Or you could go the other way, and that's what society did. And the other way was to say, no, you just are an expert in a very narrow topic, and you keep drilling deeper in that. So I think that a lot of this culture that we have to address is to recognize contributions of teams, and how actually by working in teams, individuals rise to their highest contributions.
Thank you very much, Marcia. Anyone else would like to have a question? May I invite Professor P.S. Goel, he's the chairman of our research council. Yes, sir. Professor Goel, please go ahead.
Ma'am, I'm an engineer, and just want to give a perception of engineering. See, the same term, what you call in convergence, we call it system engineering. And when we make any product, whether it's a rocket or a satellite, or even a simple thing like cell phone, the amount of cross engineering that goes into those products is so huge. If you are talking about making a car, in fact, not only engineering, you have a aesthetics, you have a social engineering in that, you have a marketing perspective, you have so many things. So point of saying that perhaps the term which we use in engineering is a social engineering, system engineering, which perhaps is more or less equivalent to what you're talking of a convergence in geosciences or generally in science. I'm not sure whether it is correct or not.
I think there's some truth to what you said, but convergence, systems engineering. Let me tell you a little story about systems engineering. When I first became director of MBARI, the Monterey Bay Aquarium Research Institute, the engineers were divided into the mechanical engineers, the software engineers, the electrical engineers. And when I arrived, I created a new group of systems engineers. It turns out everyone wanted to be in the system engineering group. And the reason why was the systems engineers were the ones who had their fingers on the pulse of the users. And they understood best how to take what the user needed and translate it into the system design to actually deliver that. And that was the most rewarding part of it. Other people were just seeing little pieces of it, whereas the systems engineers actually got to design the whole system. Now, I think the difference between convergence and systems engineering is you know exactly what you want to end up with. You know that you want to end up with autonomous underwater vehicle that has integrated artificial intelligence such that it can find anomalies in the ocean, sample them, map them, and bring them back to shore. And if in the systems engineering process you end up with something else, then you've clearly not done your job. Whereas in convergence research, you only know where you started. You don't know what you're going to end up with. And so it truly is research in that the outcome may not be predicted, but you just know that the radical fusion of these new fields will bring upon unexpected and important new discoveries. So that's how I describe the difference.
That's a wonderful reply. Anyone else would like to ask a question? comment. Yes, Professor Harsh Gupta, who is former director of NGRI and also secretary Department of Ocean Development. Yes, sir. Over to you.
Well, Marcia, first of all, thank you very much for such a wonderful talk that you gave this evening and this morning for you. And I really liked your concept and the requirement of merger of science with society and social sciences so that the benefits can reach the grassroots. And you gave the examples of earthquakes where the two ends are missing totally. On first end, we still don't know what really happens uh, near earthquake sources because somehow, because of geographical, geophysical, and other limitations, it is very difficult to observe earthquakes in near field. So that part is missing, and all our models, etc., have been not yet verified. On the other hand, we see that the deaths due to earthquakes are on increase in spite of all our developments. In the first 20 years of the 21st century, we have lost more human lives in earthquakes and resultant tsunamis than the entire 20th century. But at the same time, there are some very good encouraging things. For example, the 2010 Haiti earthquake took 300,000 lives. It was only magnitude 7.2. Whereas the 14th August earthquake just last month was 7.2, but the lives lost were much less. Of course, the location was different. So a change is being brought out. Only thing is this, that we have to work more and more to work on both these ends and really get into the social aspects, as we rightly said. And at one end, we try to find out exactly what is happening. And that's why specialization becomes extremely important. On the other hand, we need to really digress our information or meet with everything else so the results of our work reaches the masses. Thanks again for your wonderful talk.
Okay, so you had so many rich areas of discussion in that question. I'm just going to try to touch briefly on a few of them. First of all, predictability of earthquakes. That is, of course, something that we all understand. We are not there yet. Yeah. And my own personal view is I'm not sure we ever will be able to predict earthquakes. And let me tell you why I think that. First of all, I think that earthquakes are a classic example of chaos. And as you know, in chaos theory, there are sometimes certain qualities that you can predict about the earthquake, but you may not be able to predict its moment of initiation. And as an example of why I believe that, California is very well instrumented with seismometers, some places very densely, such that we can get earthquakes of magnitude less than 1, and we can measure them. And what we know from that that network is that small earthquakes are happening all the time, everywhere. And so the question is not when does an earthquake start, but when does it stop? Which ones remain magnitude 0.5 and which ones trigger a cascading event that becomes the magnitude 8? And whether we will ever have enough understanding of all of the asperities on fault zones, all of the fluid flow, the entire history of that fault to be able to predict it is a question. And then I say, even if we could predict it, what would we do? If you could predict that a small earthquake was going to cascade into the big one, you aren't going to evacuate New Delhi. You aren't going to evacuate Los Angeles. You would cause more deaths trying to do that than probably from the earthquake. And that is why I think all the focus in earthquake risk reduction has not been in prediction, but instead has been in the building infrastructure. And a beautiful example of that is the Haiti earthquake of 2010 and the Chilean earthquake, the magnitude almost 9 that happened off the coast of Chile. Those two earthquakes, if you look at the Mercalli shaking on land for both of those earthquakes, patterns were very similar. Even though one earthquake was bigger than the other, its effect in the populated region, they both had the same Mercalli intensity of shaking.
Yeah.
And if you put 400 people in a room and shake it up in those earthquakes with that Mercalli intensity, if they live in Port-au-Prince, one person walks out of that room alive. If you put 400 Chileans in that room and shake it up to that Mercalli intensity, 399 people walk out of that room alive. And the difference was building codes. And of course, the ability to enforce the building codes. Chile is a country that has very strict building codes. One building collapsed in that earthquake, and the construction company that built that building, the owner is probably in jail. That's how strict they are on their codes. So I agree with you that while deaths may be rising, it's because more people are living in hazardous regions. And unless we invest in the infrastructure to keep them safe, the death toll will keep rising.
True.
Thank you, Marcia. That's a very interesting reply, but I assure you that you have stirred a hornet nest, I would say, because there are a lot of researchers still hoping that earthquakes can be predicted someday. And yeah, fine. So anyone else would like to ask a question? May I request Professor Chandrima Saha, Madam, would you like to say something? All right, anyone else? Maybe research council members?
You see, I have one query.
Yeah, please. Yes. Dr. Tiwari. Yes.
I was just going through your presentation and a bit really trying to understand that when you put a discussion on sustainability, there is a point of having historians. And if we see the historians, we learn from the past, but when we talk of geological past, it is in thousands of years or millions. Historians are talking of only a few hundred years. So in sustainability terms, what do benefit we get from historians?
Okay, so let me give you a very specific example of that. When I started out in the geosciences as a graduate student, the word all around the street that people were talking about was copper, and how we were coming to the end of Earth's reserves of copper, and we would not be able to build telecommunications cables and information lines and things like that because we were running out of copper. But then what happened was fiber optics was developed. Fiber optics is made of silica. Silica is one thing that this planet will never run out of. And so it just shows, I think we learn from history that the solution to scarcity might be innovation, not necessarily recycling or whatever. It can be innovation by replacing scarce resources with more abundant. Another thing that was very common when I was a graduate student, people were predicting the end of oil. That peak oil had already happened, and we were already on the downslope of oil. And then, of course, fracking was developed, and all sorts of new reserves of oil and gas were made available. Now we're at the point where we have so much oil and so much natural gas and other fossil fuels that we will definitely cook the planet before we run out of fossil fuels. So that's why I argued historians. Historians have to keep us honest about how we are not necessarily making all of the right predictions because we have too narrow a view.
Thank you very much. We had really made our.
I can't raise my hand, but can I ask?
Yeah, thank you. We will end up with Professor Saha's remarks. In fact, this week has been very rewarding having you, Professor Saha, speaking to all of our colleagues. And incidentally, this week on first, we'll have our paper appearing in Science on cascading events in Himalaya. So that will be really
good.
Thank you. I would like to thank Marcia for giving such a wonderful lectures. And I just had one small question. That you said that earthquakes are happening all the time. I mean, I'm not a person of the field, so I won't know. So sometimes we do feel something is happening, but it's not recorded in the Richter scale. So is it possible to predict from the number of small earthquakes that are happening in a place in predicting larger earthquakes that might happen?
Yeah, so a very good example of where that has been remarkably successful and reduced risk is with volcanic tremor. The small earthquakes that show that lava is moving underground towards a caldera and filling up the volcano before an explosive eruption. And by properly instrumenting volcanoes, geophysicists are able to monitor the motion of the lava and predict when the eruption is going to be. And that's all part of the volcano disaster program, VDAP, that the USGS runs and tries to help nations like in Indonesia and other places instrument their volcanoes so that they can save lives. To date, that same technique has not been as successful in earthquake prediction on faults that mark the tectonic plates. There have been cases of clusters of earthquakes that happened, small earthquakes, and then they died out and nothing happened. Other cases where they actually formed a foreshock sequence and a major earthquake did happen. There's a beautiful example from China where the Haicheng earthquake was predicted by monitoring small-scale seismicity, and the Chinese government was able to evacuate the city of Haicheng. They moved everyone out into the field to spend the night in the open in the northern Chinese winter, and the earthquake happened at night, and the village was the whole town of Haicheng was saved. Because of that, geophysicists thought, oh, earthquake prediction is right around the corner. We'll just do what the Chinese did. But then it wasn't long after that the Tangshan earthquake happened and killed 500,000 people. And there was no warning to that one, even though they were trying to do just what happened in Haicheng. So there have been some successes, but unfortunately not consistent.
Thank you. Thank you very much.
Thank you.
Another example of history, why history is important.
Thank you very much, Marcia, for the reply. I think Dr. Tiwari, I think we can.
Yeah, please.
Yeah, but before that, I would like to just ask one thing. Do you think it's time to incentivize convergent research programs and start the convergent research journals?
Well, yes. So there have been several journals that were started with the idea of convergence. So Science Advances is actually broader than science in order to attract convergent research. At the National Academy of Sciences, we have just started a new journal, which is launching early next year and is open for submissions right now. And it is broader than PNAS because it includes engineering, it includes health medicine. And so the idea for this new journal, which is called PNAS Nexus, is to be the nexus of all of these different fields in order to capture convergence. So I think there definitely is a role for new journals. And I forgot to say congratulations to Professor Shah for her election as president of the Indian Academy of Sciences. I really look forward to working with you.
Thank you so much. Thank you so much.
Thank you very much. I would just like to say that, as Dr. Tiwari mentioned, our work on cascading hazard effect is appearing in Science 1st October issue. If I had heard your talk before, probably we would have done it slightly differently, but maybe we will definitely look into this new concept and new approach. So thank you, Marcia. I think that was a fantastic, wonderful lecture. Very thought-provoking, and I'm sure our scientists will definitely try to apply these new ideas in the future research. Thank you very much. And I'm also...
Well, it was a pleasure for me. It was a pleasure for me, and the questions were terrific.
Thank you very much. And of course, our Director General, Professor Mande, has been very kind to join us, and he has sat very patiently and with a lot of interest. He has attended the talk, and